I'm Rob. I'm going to give you a bit of insight this morning into my work on the development of liquid processable BT resins, and more specifically, and how I'm applying those into composites. So what are BT resins? It's basically a combination of two different resin systems to bring together the beneficial properties of both. So we're combining cyanate esters with bismethamides in order to achieve matrix resins with low dielectric constants and really high temperature performance. So TG's around 300 degrees. And this makes them attractive to be used for things like printed circuit boards or in radomes for aircraft. But the problem that holds back a lot of these systems is the processability. So typically you'll need toxic solvents in order to get them into liquid form, or high temperatures, so these things melt at about 140 degrees. So we want to try and develop a system that you can use at room temperature to infuse onto fibres. So that's what I've done, and I've developed a liquid processable BT resin. I'm not going to go into the chemistry of how I did that here, because this is more about the composites, but this slide just summarises some of the basic performance properties of getting out of it. So this is a photo taken at room temperature, so you can see there, it's a liquid, and that's backed up by the rheology plot in the top left, so we're talking viscosities below 1000 millipascal seconds at room temperature, so that's low enough for infusion. We've got a large processing window of around 150 degrees because the onset of reaction doesn't start till you get to about 140, 150. And in cured properties, we've got a tan delta peak on our DMA plots of 280 degrees for TG and a high degradation temperature. So this is the resin system we want to use, and I now want to take it forward and apply it onto fibres. So what fibres to use is the next question. The first thing is that we're not using carbon here, because the electrical properties of carbon are completely unsuited to the applications in mind here, so we're focusing on glass. I also wanted to have a look at what kind of sizings we could use and how they might affect the properties of the composite we get out of it. So in this experiment, I basically did an infusion with 3 different kinds of glass fibre, well, the same fibre with different sizings. So we've got unsized fibres, aminosilane functionalised fibres, and volan functionalised fibres, and these are expected to interact with the different components of the resin in different ways. So unsized, there won't be much reactivity with either component. The aminosilane should interact and form bonds with both, and the volan just with one component. So we got these fibres and we prepared our layup, and we did a room temperature infusion. This is the setup we used. So we've basically got your standard sort of infusion setup where you've got your inlet coming in, distributing the resin using a mesh across the fibres, and before pulling it through them and pulling out the outlet at the other end. As you can see here, we did the infusion of all 3 panels in one go in the same setup. This enabled really tight control over ensuring that every sample had the same pressure and the same batch of resin to make sure there's no inconsistency there. And we managed to infuse all 3 of these plates at the same time in about 5 minutes before putting it into the oven to cure it. So that's the infusion, and we got some nice samples at the end which we can then test and check the properties, and if you do want to come and see some samples, I've got them by my poster. So to investigate how the sizing might have impacted on this material, we looked at short beam shear testing, and you can see straight away from the graph between the 3 different fibre types you're getting quite different responses, particularly in terms of the maximum load you get out of there. So from the table you can see that there's a difference of around 20 megapascals between the best performing and worst performing material. What we also noticed was that different sizings led to different manufacturability of the plates. So unsized fibres, very difficult to handle, ended up with warpings and things like this in the fibres. And with the aminosilane functionalised fibres, we noticed a higher void content in the samples, maybe caused by the sizing affecting the permeability of the fabric. So overall, this showed us that for future work, the volan fibres would be the way to go. So basically that's just a short bit of my work. We've managed to make composites on a small scale, and we've discovered the best sizing that we're going to take forward into future trials. There's quite a lot of future work here that can go on. The first thing I'm currently doing is microbond testing, so to fully characterise those interfaces and figure out what the difference in sizing is actually doing on a microscale. And then we're going to scale it up, making bigger panels, which I'm doing at the moment with the NCC, full testing of the composite, with the ultimate aim of producing a radome demonstrator. So we've got funding to create some demonstrators which are going to be 1 metre by 1 metre, a proper part, and hopefully prove that this can actually be useful for an end application. So thanks everyone for your time. If you've got any questions, I've got time for a couple of those, and if not, come and find me by my post in the door. Thanks.